FusyBot. So here I am after so many days, and we'll be going to implement RRT star today on my 5 degree of freedom DIY manipulator. So here you can see it's my DIY 5 degree of freedom manipulator. It's been equipped with 5 servo motors. Now we'll see whether RRT star will able to plan a path and move this robot. Okay, so let's start. So before starting, I just want to tell you, you can see on my screen I have made a Mojoko digital twin of the same actual robot, so that we can also see and visualize in the virtual how it actually acting. And it is also beneficial for me to test the features before implementing it to the actual hardware, as it can save my hardware. Okay, so we'll move further now. Before starting, I would like to explain you what is RRT star. And to explain you, I would like to take a toy problem here. So what is my toy problem? Basically, in simple XY plane, we'll try to move from point A to point B. That is the whole concept of RRT star, right? In RRT star, we have to move from A to B, avoiding the obstacle that are in between those 2 points. So yes, now you can see on my screen that there is a code for the implementation. This is the RRT star. I will explain you very fast. I would not like to bore you with the code and all, but I would like you to take a look on this graph, that how RRT star has made a plan from A point to the goal point with these obstacle in between, and it is in XY plane. So it is a 2 degree of it's a 2-dimensional plane basically. On the left side we have A star. We'll not focus on the A star today, but definitely I will going to make a video on A star too, and then we'll see which one is better for which type of application, right? So I will give you a quick glimpse about what is happening, and with this I would also explain you what is RRT star, right? So RRT star, basically RRT is 4 steps, right? It's a random sampling algorithm. So it contains all the 4 steps. First point is find a random point. Then you can see here we have just find a random point with some width and height of our workspace, right? Then find the nearest point in my node. So that point is obviously nearest to one of the point which are already there in my node. We have find that point. Now we have to move in that direction with some step size, right? So I'm moving in that direction with some step size. Okay, now see if that point is in collision or not. Okay, if it is in collision, we'll continue to iterate for the next iteration. But if it is not in collision, then we will add it to my node, right? So this is simple RRT. Now what is the difference between an RRT and a RRT star? So RRT star has basically some modifications which were not there in RRT, right? So how RRT star works is, after sampling that point, before adding it to the new node, it basically tests the best parent for that node, and then rewire that point to become a parent of any other node, such that the cost will be reduced. So the next step is the rewiring point. What it basically does is, whenever I have a point, I always see whether it is possible that the new code wala distance plus the already distance which I already have is smaller than any other neighbor. So I have a neighbor radius. So for suppose I have a point, this is my new point, and I have 5. I will see whether coming to this point plus the distance, that is the position of the node plus new node, is smaller than the node cost, that is any neighbor's cost. If that is the case, I will update my current point as the new parent. Okay, so I will update that node to this new point, such that we are rewiring it. We are rewiring the previous parents also. So in this way, then I will see whether it has come to the threshold of my goal. If it has come to the threshold of my goal, then it's fine. So this is the basic algorithm. I think it's getting boring, so let's see how it actually works in the real 5 degree of freedom manipulator. So this was just a toy example to make you understand what RRT star is. So this is how it finds a path. Now let's start with the real 5 degree of freedom manipulator. So this is the small UI I have made to operate this 5 DOF manipulator. So let's start. So this is the current position of my robot. Okay, so I will give some points. So let's suppose I will be going to 85 degrees angle, and then here I will be going to somewhere around 45 degrees angle, right? So let's plan the path and see what is happening. So I will hold it. It is not tighted on the base, so I will hold it. See, this is RRT star, and the time is so while. Now I will try to go back to the previous point where I was. So it's 55, and then 85, and then I will try to reduce the time and see how the digital twin and this is working. So you also have to see on my screen. So for suppose I want to go it in 1 second, I will publish the command. I think you can see it's move. So yes, RRT star makes a robot move, but how does it happen? So for that I want to show you the code of RRT star that I wrote in my C++ pipeline. Okay, so basically this is my RRT star algorithm. As you can see, it's the same algorithm I already told you. It is having those 4 and 5 steps only. Okay, so this is the plan function, RRT star plan function. I will call this function, it is almost same, right? So I will start with a random sampling. I told you I will sample a point. Then there is a goal bias here. So I will explain you what is actually a goal bias. First we will see what are the points. Then I will find the nearest point which are already there in my node. I find the nearest point, then I find the direction I have to go to that point with my step size. So this is what it is doing, right? And then the next step is choosing the best parent. I will see out of the neighbors, all neighbors I have, which is my best parent. So that way I will choose the best parent. You can see that is what I am doing here. From all the neighbors I am finding, okay, if there is any possible name, if there is any possible parent which is having lesser cost than this, if that is fine, then we'll rewire it. We'll see if my new node can become a new parent for any other node and reduce the cost. Yes, if it can do, so I will rewire it. Okay, then there is a goal check. This is the simplest RRT. But I have a question for you. Do you think only RRT star can move this robot? So the answer is no. Why? Because if I am giving a point in the Cartesian space, so first of all I would like to tell you that it is a RRT star in joint space, not in a Cartesian space. Okay, so if I give any points to RRT star, it will just find some random points that will go to that point. It will plan the path. But can I directly give that plan to my robot? No, these are servo motors. I have to make a pipeline for it. And how that pipeline works, RRT star will give me some points. Now I have to interpolate to that point to get a continuous point spline in a real world. So I will either make a line joining all those points, or I will make a cubic or quintic spline over there. Then this is the path. Now the path is RRT, but now I should have a trajectory for it, like fitting the time curve on that path. So then I will fit a curve in the trajectory space. That can be a trapezoid, then can be a quintic, anything, whatever you want. So this is how the entire pipeline is there. And then at low level there is a PID control that is controlling the motors. So that is how this entire pipeline works. So now again a question comes. So if I tell you that this is not a complete RRT star, but then you might have a question, why is it not a complete RRT star? Because there is a very important part of RRT star, that is collision avoidance. So whether my robot will able to avoid any collision. So let's put some obstacle in here. So for suppose I am putting an obstacle in here, right? So I will try to move my robot and see whether it will able to do it or not. So let's suppose I am doing it 30 degree, and then this is 45 degrees, and then here I am going minus 70 degrees. Let's see what will happen. So it came here, right? Okay, so it's not a complete RRT star. Why? Because the collision avoidance is currently not there. How can you say that? So I will show you. So let's suppose I am giving it an angle of minus 70 degree to joint one. I will hold this. You can see it collided with this, and it is not able to plan a path that can avoid the collision, right? But then how can we say it's a RRT star? So yes, it is not a complete RRT star for now. But in the upcoming video, I will show you how I can add the collision to my manipulator, and basically how a Cartesian obstacle can translate to a joint obstacle. That I will show you, and I will show you how it behaves with RRT star in joint space with obstacle. Then we will move to RRT star in Cartesian space, and then we will see what is the difference between two and why RRT star in joint space is preferred in case of manipulator. Okay, I think that's it for this video, but there are lots of videos which are going to come, which will show you the implementation of actual algorithms which we basically learn during our study, like RRT star algorithm for path planning. Then we have different type of trajectory planners. Then we have inverse, like how do we solve the inverse kinematics of a real system like this, how we solve the forward kinematics of a real system like this. So stay tuned for that, and thank you for today. Bye bye.